everyone. So, okay, there was some message. Yeah, okay. Okay, so let's begin again. Hello and welcome everyone to this lecture of this Harishchandra seminar series. We are glad to have Manish Mishra from IISER Pune today with us. He will give a series of 3 lectures, out of which today is the first lecture. Today he will speak on Bernstein decomposition, types, and Hecke algebras. Over to Manish.
Thank you, Amiya. So let me share my screen. Allow Zoom to share your screen, open system preferences. Oh, so Zoom, okay, on. And now it should allow me to share. Where is QuickTime? What? Security and privacy. But I did. Oh, I see. I have to enter some password. I'll have to do it. I'll have to join the meeting again, I think.
Okay, go ahead.
Okay, let's try this time. QuickTime, where are you? Yes, this is okay. So are you able to see my screen?
Yes, Manish.
Okay, great. So let me begin this basics of type theory. So I'll start with the very beginning, where I'll describe basic notions of category of smooth representations. So we are going to learn theory of types. So let G be a connected reductive group over a non-archimedean local field F, and let Rg denote the category of smooth representations of GF. So I'll recall the notion of parabolic induction. So let M be an F Levy of the group of G, and P is a parabolic and F parabolic with the Levy factor M. So there is an induction functor which takes the category of M to category of G called parabolic induction functor. So this, so I'll describe this functor. So this takes a representation sigma with the space realizing sigma being V sigma to a representation iota sigma with the space realizing being denoted as iota v sigma. And this is called parabolic induction functor. And it's explicitly described like this. So the space of this functor consists of those functions from GF to the space realizing sigma, such that F is locally constant. And F transforms like this. MUG is equals to sigma M FG. So what you're doing is inflating the representation sigma trivially to the parabolic and then using the usual induction. So this is for all M in MF and G in GF. So this space of functions has an action by right translation. And so this functor admits a left adjoint called Hecke restriction. Okay, so the restriction functor, it takes the category from of the smooth representations of G to the category of smooth representations of M. So the explicit description of this is simply the co-invariant, taking the co-invariant. So restriction of V sigma is simply V sigma co-invariant with respect to the unipotent radical of the parabolic. So please stop me if there is any question. Are there any questions?
I guess no questions so far, Manish.
Okay, just making sure because
Sure.
in online it doesn't. It's like talking to yourself.
Yeah, yeah. So I will stop you in between if there is a question.
Sure, yes.
Yeah.
So I'll now recall Frobenius reciprocity. Says that so it's basically saying that there is a left adjoint. So it's a tautological thing. So I should be consistent with notation. So the tautology is simply that this is df by sigma. Okay. So Frobenius reciprocity says that the description of Hecke restriction that I have written here is actually the left adjoint of the induction. All right. So now let's talk about an important involution called contour gradient. So there is an involution on the category of smooth representations, which is simply sending by representation to its dual representation. It's not, I have not written it very, so this is contour gradient. So there is an involution which sends representation to its contour gradient. So now I'll describe what is contour gradient. So you take the dual of this representation V and take the smooth part of it. So pi star is simply pi dual and then I'll say smooth part of the dual representation. Okay, so the dual representation that is obviously a representation, but it may not be a smooth representation. So every vector may not be fixed by a compact open subgroup for some compact open subgroup. So so you take the smooth part, and in this way you can come up with an involution on this category. The problem is that this involution is not respectful of induction functor. So this is not well behaved with respect to this this involution. What it means is that if you take the dual of the involution, contour gradient of the induction, and if you take the other way, induction of the contour gradient, then these two may not be equal in general. All right. So what it says is that you have to so this is iota. What it says is that you have to modify iota a little bit so that you can have this very nice natural property. So to do that, we define a normalization of this induction. So let delta P is our parabolic subgroup, be what is called the modulus character. So it's an unramified character. Unramified I haven't defined yet, but it's a character from the parabolic subgroup to this determinant of the adjoint of P. So here, where this U is the Lie algebra of the unipattern radical of the parabolic. Okay, so P, every element of P acts on U, and therefore it acts on the Lie algebra of U. So that is what I'm calling add. And then you can take the determinant of this linear operator and then take the norm of that. So you get a number, and in this way you get a character. So you get a complex character, and so this is trivial on U. On U, and therefore it's independent of the choice of P for a given Levy M. Now define normalized induction to be this modulus character square root. So now you have a new induction. So first you take the representation of the Levy, inflate it to the parabolic trivially, and then multiply it by this character, and then induce it all the way. So this is called normalized parabolic induction. So just like we define normalized induction, we can define normalized Jacquet restriction. Which is delta P half and then GF. So these two are now well behaved with respect to taking the contra gradient. So you can take the contra gradient first and then apply induction or restriction, or the other way, and you get the same result. So now let's introduce some notation, which is so we call irg the irreducible objects of the category of smooth representations of G, and also we'll use notation and write star, we'll write check to mean star. So write pi check to mean pi star. Okay. So we will pretend that we are not taking the smooth part while we actually are taking the smooth part. So we now define what is called a supercuspidal representation. So a representation is called supercuspidal if this Jacquet restriction is trivial for all proper F parabolic subgroups of GF. Okay, so so those representations which have no part trivially arising from a smaller Levy subgroup. So such representations are called supercuspidal, and they are the building blocks of this category. So these are like the atoms of this category of smooth representations. So this I'll explain that so the whole thing boils down to understanding these supercuspidals and how the induction functor reduces. So to understand RG, it amounts to understand the supercuspidals and the reducibility of the parabolic induction. This gives you everything, the full categorical structure of the of RG. So a priori, one wouldn't know why would there be a supercuspidal representation of a given group at all. So it could be that um, everything is arising out of a torus. So why would how can we say that a given group has any supercuspidals at all? So this so the theorem is that they do exist. Exist for any reductive group G, reductive F group G. So this result has been known to people since the beginning of this theory, but there were not proofs. Then there were two successive papers came in quick succession, which gave some partial results. And then very recently, me and Jeff Adler gave a first proof for the existence of supercuspidals, which we so so although this result has been known, but I think the literature was missing a proof. So we provided that. So now let's move on to the next part. So we want to understand cuspidal support and unramified characters. So let's define those things. So if tau is an irreducible object of G, of RG, then in this basic theory, you learn that tau is a subquotient of a parabolic induction of a supercuspidal sigma of the approximal points of a levy. Moreover, if this pair sigma m comma sigma is given tau, the pair m comma sigma is uniquely determined up to conjugation. By GF. Okay, so this pair is called the cuspidal support of tau. So now I will talk about the notion of unramified characters of a group. So you are given a connected reductive group H. And to that group, there is an associated lattice, which is simply this. GM is one-dimensional multiplicative group. And now one defines a homomorphism, which is called nu H, from the F points of H to this complex numbers, which is sends a point H to the not complex numbers, but this space of functions. So it sends a character to negative order of chi H. So this is called Brouhard-Tate homomorphism. And the kernel of this homomorphism is an important subgroup. So we denote by not H F the kernel of the Brouhard-Tate homomorphism. So let's see an example. If H is a torus, then not H F is simply the maximal bounded subgroup of HF. And if H is a semi-simple group, so if H is its own derived group, then this not H F is simply HF. So, for example, in SLN, it's a semi-simple group. So the kernel of Brouhard-Tate homomorphism is everything, the full group. Now we define the group of unramified characters. So let X and R H be those characters of HF for which the restriction to the kernel of Brouhard-Tate homomorphism is trivial. So such characters are called, so this is a group, it's an abelian group. It's called group of unramified characters of HF. So now let H hat denote the complex dual of H. So what does it mean? So so H comes equipped with a root datum. You can dualize the root datum and choose a field to be complex numbers, and then you get a corresponding group, which is called the complex dual of H. And the unramified characters, the group of unramified characters of H can be described in terms of this complex dual. So there is an isomorphism, which is the center of the complex dual, and then you take the invariants under the inertia, then you take the co-invariants under the Frobenius, and then you take the identity component of that. So I'll write down Z H hat is the center of H hat, I n is the inertia, and Fr the Frobenius. So from this, so center of this H hat is a subgroup of altori. So it's in particular a tori. So this whole thing is a tori. So in particular, the group of unramified characters of H has the structure of a complex torus. So now we have defined a lot of notions. So we move on to Bernstein decomposition, which describes the categorical structure of the category of smooth representations of G. So let M be an F Levy of G and sigma a supercuspidal representation. Now you form an equivalence class of these pairs M comma sigma, and this class consists of all such pairs such that they are the same as M comma sigma up to twisting by some element G, up to conjugation by some element G, or an unramified twist of the Levy M. So this is what is written here for some G in GF and nu in the character group of unramified characters of M. So for each pair, we have associated a class called M comma sigma square bracket G, and the collection of such classes, the name is called the Bernstein spectrum of G, and it's denoted BG. So now let's define a full subcategory of the category RG. So let R M comma sigma G G to be the full subcategory of RG. So full subcategory meaning close under taking subquotients. So this is the category which is built out of all these representations made by taking parabolic inductions and its constituents, and where P prime is equals to M prime U prime, and M prime comma sigma prime is an element of the equivalence class M comma sigma square bracket G. So you take any element of the equivalence class and then you do parabolic induction. Then you take all the constituents of the parabolic induction and then take the extensions of them and then thus build a category. And this category is a full subcategory of RG by construction. And this category has a name. Is called a Bernstein block. Associated to M comma sigma. So this is the Bernstein block associated to this Bernstein spectrum element M comma sigma. And the main result of this, beginning result of this theory is this fundamental result of Bernstein. Which says that the category of smooth representations of G is the product of Bernstein blocks. So it's a product of these indecomposable subcategories. So you cannot factor R as G further into subcategories which are closed-ended subquotients. So this is the finest decomposition of RG, which is into full subcategories. So let's see the most trivial example of this setting. So let T be an F torus. Then the Bernstein spectrum of T, this corresponds to simply the characters of the maximal bounded subgroup of G, and all characters of TF are supercuspidal, and what is this Bernstein spectrum element? It's simply T comma chi nu, where nu is unramified. So nu ramified. And so this is so these are the Bernstein blocks for the torus. Okay. So if you choose a character of the maximal bounded subgroup, then there is no conjugation action here, only twisting action here. Conjugation is triggered, so there is only twisting here. So blocks are just twistings. Okay, so now let's go to more general setting, which is supercuspidal blocks. So we saw that in the case of a torus, all blocks are supercuspidal blocks. But more generally, we can look at these blocks, G comma pi, G. So instead of, so for the Levy, you're taking the full group G. And so we want to describe this block. So we want to describe this. Okay, so that's our objective. So take pi and restrict it to the kernel of the Brouhard-Ritz homomorphism. So this is a finite direct sum of irreducible representations of GF of not GF, all of which are GF conjugate. Now, so now fix an irreducible constituent under this decomposition and call it not pi, not pi and W. Okay, so we are restricting pi to the kernel of Brouhard-Ritz homomorphism and then picking up an irreducible constituent which we are denoting not pi. And now build this representation of GF, which is simply the normal usual induction of not pi to GF. So this is a representation of GF and the isomorphism class of this capital pi is independent of the choice of not pi. Okay, so in this way we have cooked up a canonical representation associated to Bernstein spectrum element. So now if you are given a representation V in the Bernstein block, then this this object is naturally a module of an algebra and GF pi module. So why is it an endomorphism and a module of this endomorphism? Because this where is the pointer? This one. So it it acts on the this algebra acts on pi, and therefore this object is a module of this algebra. So so specifically, so more precisely, the action f dot t is f naught t, where f is home and t is an endomorphism of pi. So so this is a right action. So it's a right module of the endomorphism algebra. So this home object is a right module of the endomorphism algebra, and hence we have a functor. I'll call it f pi, which is from the category, which is from the Bernstein block to the module category of the endomorphism algebra. So in this way we are sending we are setting up a functor from the category of groups to the category of modules of an algebra. And the important thing is that this functor is actually an equivalence of categories. F pi gives an isomorphism with inverse being module is sent to the tensor product. Okay, and where this object is seen as a representation of GF by its action on this capital pi. So we thus have an equivalence of categories, where one category is the Bernstein block and the other category is the module category of an algebra, which is an endomorphism algebra. So this pi is called Bernstein projector, and we have established an equivalence of categories in the case of supercuspidal blocks, and this generalizes to an arbitrary block, which I will describe in a moment. So before that, I will make a remark that this algebra that we have described just now, which is the endomorphism algebra of the Bernstein projector, is commutative if quite often. So if pi restricted to not GF is multiplicity free, and this is often the case, happens if pi admits a Whittaker model. Okay, so this is quite often the case that you're dealing with representations which admit a Whittaker model, and therefore you are generically in this situation where this endomorphism algebra is commutative. So just be careful that we are looking at the supercuspidal block setting at the moment. So when we go to a general block, the endomorphism algebra will be highly non-commutative. So now let's go to the general case. So let M be F Levy and sigma a supercuspidal of MF, and P is a parabolic subgroup, F parabolic, with unipotent U, and choose not sigma, an irreducible constituent of this supercuspidal restricted to the kernel of Berhampur homomorphism, and put sigma to be the usual induction from not sigma to MF, and put capital pi to be the parabolic induction of this sigma. So this object called Bernstein projector this is the general case, and this is independent. So this is canonical. So it depends only on the Bernstein spectrum element. It is not dependent on the choice of this irreducible piece, not sigma. It only depends on the equivalence class of m comma sigma. And just like in the supercuspidal block setting, you have an equivalence of categories. Which is m comma sigma g to the module category of the endomorphism algebra of the Bernstein projector, which sends a representation to the object, which is a home object from the Bernstein projector to that representation. And this gives this functor gives an equivalence of categories. Categories with inverse. Being a module going to tensoring that module with Bernstein projector. So in this way, we are able to see Bernstein blocks as module categories of certain algebras, which are these endomorphism algebras. So since so if we know the algebra, then it's supposed to be a simpler problem. So the question of describing these Bernstein blocks reduces to the question of describing the module categories of these algebras. It turns out that these algebras are have a very nice presentation, and they can be quite elaborately described. So this is the whole focus of the remaining two talks. So this is what remains to be done in the next two talks. So let me just complete the notation building that we are doing at the moment. HS is our endomorphism algebra of this pi s. So I'm writing pi s because it only depends on s. Okay, and where are we? Okay, so the next thing will be type theory. I guess it's a 1 hour lecture.
Yes, Manish.
So next thing will be type theory, and then I'll describe a Hecke algebra associated to a compact open datum, and describe the Bernstein block as the endomorphism algebra of another object, which is maybe say Bushnell-Kutzko projector. And so in this way, you are able to describe Bernstein block as endomorphism algebras of a priori two different types of algebras. And then the next result will be that you can control the choice of types so that these two algebras are isomorphic. And then, so then we will be in a footing where we want to describe that algebra. So this is the subject of Hecke algebras. So I want to finish here for today.
Okay, thank you, Manish, for the talk. So are there any questions or suggestions or comments? I guess he has used many notations, so especially the students, you can freely ask any further clarification on any notations or any other things. Okay, if not, then let's thank the speaker virtually.
Thank you everyone for the patience.
Okay, so yeah, I guess we are kind of done for the day. But Manish, just before we finish, I want to ask you a general question.
Sure.
So in nice case, when we relate these two algebras, like Bernstein projectors and the other compact Hecke algebras.
Yes.
So equating these two Hecke algebras, then what kind of information we extract for the representation? If we can relate these two, do we get something new or interesting out of this relation?
So these endomorphism Hecke algebras, they look very much like Iwahori Hecke algebras. the
Right.
classical case. You know, so the important thing is that but we have done recently with some collaborators, Jeff Adler, Kazuma Ohara, and Jessica Finzen, is that any Bernstein block is equivalent to a depth zero Bernstein block. So you can reduce the problem to a depth zero Bernstein block, and there you can describe the Hecke algebra very well. So and the Hecke algebra looks quite close to the usual one, and so and the module category has been extensively studied in the literature. So
Right.
so in this way you get a very good grasp on the problem.
I see. I see. Okay. Thank you. Thank you, Manish.
Yeah.
So anyway, thank you everyone for joining us. So
Okay,
maybe we'll
I'll see you then.